So basically, this is our last lecture. I think the original plan for this lecture was to be something like applications of p-adic Eichler-Shimura, but we're a bit behind schedule, and so instead, the plan is going to be first to sort of review and really introduce the classical and p-adic modular forms for the coherent and Betti point of view. So in particular, we haven't actually defined the p-adic modular forms from the coherent point of view. And then it will be to kind of explain p-adic Eichler-Shimura from this point of view. And I will do my best to kind of give a, I don't know, kind of fake explanation of how the stuff that Vincent explained last time is used, and then I'll also do my best to explain what are the correct statements. That's if all goes well. If all doesn't go well, then okay. So, and I have to apologize about one more thing, well, two more things. One is that we're a bit behind on the notes, but we will write them. And so the other is that I'm only going to talk about the modular curve, and I found when preparing this talk that I'm incapable of consistently calling the modular curve S. It has to be X. And so I'm just going to use that, and I apologize if that's inconsistent with the previous talk. So we're only going to talk about the modular curve, and we're only going to do integral weights just for simplicity, although that's really the most interesting case. So I'm going to have the sort of schematic open and closed modular curves. I'm going to have the sort of, so these are maybe over Q. I'm going to have the sort of finite level adic one, which I'll try to write as more curly. And this, the compactified one, and this is going to be over SPA, CP, OCP. You can, of course, view it over QP or whatever, but that's good for us. And finally, we'll have this sort of perfectoid one, which I'll denote XKP. And sort of as in Vincent's talk, this has a structure sheaf, which is the kind of completed or the continuous one. But then there are two other structure sheaves. So in addition, there's this OKP smooth and this OKP LA. Okay, so the first thing I want to do is basically explain what are the p-adic modular forms from the coherent point of view. And Vincent was about to say this in his last lecture, but didn't quite. But let me go ahead and do it, and I'll also kind of remind you of all the notations. So let's do the sort of coherent story. So my weight is always going to be an integer today, and so for k an integer, I get this sheaf, omega k smooth, which is a sheaf of OKP smooth modules. And the definition of this sheaf, as Vincent gave last time, is that it's just the sort of colimit over the modular sheaves at finite level, sort of pulled back to infinite level. Sorry, this should be k lower p. So pi kp is sort of the, maybe I'll just write it. It's the map going from the infinite level modular curve to the finite level one. But I emphasize that we really just pull back here. We do not take pi upper star because that would just basically be completing, okay? So it's just that. We don't complete. And so we can take the cohomology of this sheaf, and really it's just a confusing way of writing the cohomology of the finite level modular curves. So the classical forms, they are what I'm going to call HIK, just to kind of ease notation. I'm not going to keep writing the tame level because the tame level is always fixed and it's never doing anything. So what is this? And this is for I equals either 0 or 1. It's just the cohomology on this, so if you like, just on this topological space of this sheaf, omega k smooth. And it turns out, and it's not very hard to show immediately from the definition, that this is really nothing but the colimit over Kp of the classical coherent cohomology of the classical modular sheaf at finite level. And if you like, by some kind of gaga, this is really just the usual modular forms, or the usual cohomology. So but maybe tensored with Cp. Okay? And so what kind of spaces are these? Well, these are smooth representations of GL2QP, and you can even recover these finite level cohomologies by just taking invariants. So if I take HIK and I take Kp invariants, then I'll just get the cohomology, well, this guy, but at level Kp. Okay? So you can imagine that all of this is just some kind of bookkeeping regarding putting all of these spaces together into a smooth representation of GQP. Okay. So that's the classical forms. And actually, maybe I should say, okay, so we had this degree I equals 0 and 1. And of course, for most values of k, only one of these is non-zero. So maybe I'll just recall the vanishing statements. So if we take global sections, sort of H0k is only non-zero for k bigger than or equal to 0. There are no negative weight modular forms. And similarly, if you use Serre duality, this is only going to be non-zero for k less than 2. It's a bit asymmetric because Serre duality introduces the cuspidal sheaf. Okay, so for most values of k, only one of these spaces is non-zero. And the only reason, so you might wonder, why are we not just studying classical modular forms? Like, why are we also including these higher cohomologies? The point is that for the modular curve, honestly, the H1 of these line bundles omega to the k is not interesting because it's just the same as the H0 by Serre duality. But when you generalize this story to other Shimura varieties, then you have higher dimensional varieties. There are many degrees of cohomology. And what you should think is that the H0 is some kind of holomorphic modular forms. The top degree cohomology is some kind of anti-holomorphic modular forms. And then the cohomologies in between are some kind of, well, not holomorphic or anti-holomorphic automorphic forms. And if you're interested in those, then you're interested in these kind of higher cohomology groups. But admittedly, for the modular curve, they're not really interesting because holomorphic and anti-holomorphic forms are basically the same thing. Okay, so now let's talk about p-adic modular forms, finally. So what we're going to do is we're going to bring the Hodge-Tate period map into the story. So I'm going to consider my perfectoid modular curve, and I'm going to consider pi Hodge-Tate to P1. And what I'm basically going to do is I'm going to consider the Brouillard stratification of P1 and consider some kind of excision triangles for that Brouillard stratification. So in other words, I have infinity, which is the sort of Schubert cell corresponding to the identity element of the Weil group. And I have A1, which is the Schubert cell corresponding to the longest element of the Weil group. And maybe, depending on exactly what category you're working in, I should put something like C1 dagger equals infinity dagger, because we really want to think of these things as some kind of geometric objects which are kind of over convergent neighborhood of this point. But for what I'm going to say right now, this is really not going to matter. Okay, as I'll explain in a sec. So similarly, we can sort of pull them back and get a kind of decomposition of the Shimura variety, or the modular curve. So we have pi Hodge-Tate inverse of infinity, and pi Hodge-Tate inverse of CW naught. And so in the underlying topology of this space, this is closed and this is open. And so I'm going to use the usual letters, J and I, for these maps. And probably at some point later in the talk, I'm going to use the same letters, J and I, for these maps. And hopefully that won't cause any confusion. But for now, I'm only going to use these ones. Okay, so how are we going to define p-adic modular forms? Well, we're just going to take our modular sheaf and consider the excision sequence for this decomposition. So basically, we have a excision triangle, and the one I want to consider, it's really the one where the functors are all just the sort of topological functors, although one could certainly try to think about this in a more fancy way. So we're going to take this sheaf omega k smooth, and we're just going to split it up into two pieces. And so I emphasize, like, these are just the operations on sheaves of abelian groups. So this J lower shriek, it just means extension by 0. There's nothing derived or anything like that. And the I inverses are really, there's no tensoring with any structure sheaf or anything like that. Okay? Okay, and now we're just going to define our spaces of p-adic modular forms as the cohomologies of these two sheaves. And so here's the definition. So H, this thing that, well, H01, well, I like to write 1, but maybe it's better to, this refers to this 1, the identity of the vowel group, and maybe it's better to write id. But, so H01 of K is just going to be the cohomology, or the global sections, in fact, of this sheaf. Sorry, it's getting a bit illegible. And similarly, the sort of higher overconvergent modular forms are just going to be the H1 of this sheaf. And so, of course, in general, we would really be interested in cohomologies in all degrees, but what I'm going to just clarify in a second is that here there's really no H1, and here there's really no H0. And so I'm just considering the only degree in which there is cohomology. Okay? I mean, it's, for example, it's quite believable that this sheaf shouldn't have any global sections because sections are sort of required to be 0 outside, I mean, they're required to be 0 on this thing, which kind of meets every component. Sorry? For every k. Yeah, so this statement, there's no dependence on k. So k is just an integer here. And in fact, so this thing that von Sant said is that actually these two sheaves may be defined for any k in CP. And I don't want to recall the definition, and I don't even want to discuss that case in this talk. So I just consider the case where the weights are integers, okay? And so let's try to understand a bit about, like, what is the point of these spaces, and I'm eventually going to try to explain, like, why this really is just the usual, or related to the usual definition of overconvergent modular forms as defined in Illich's talk, in fact. So the first thing I'll say is that basically just by taking the long exact sequence in cohomology from this excision triangle, you get a 4-term exact sequence. And this 4-term exact sequence, it relates the classical forms and the p-adic forms. So how does it go? You have H0k, so the classical modular forms, mapping to classical overconvergent modular forms. And then there's a sort of boundary map, which goes to the H1, so these sort of higher overconvergent modular forms. And that goes to the classical H1. And so, okay, and we call this boundary map for some reason that I don't really want to explain in this talk. We call this the Cuson map, and we call this complex 2-term complex, which computes the classical cohomology, the Cuson complex. But the point is that this Cuson map, it kind of knows what is a classical modular form. Because if you have an overconvergent p-adic modular form, it's classical if and only if it's in the kernel of this Cuson map. And similarly, if you have whatever this higher overconvergent modular form is, it's classical if and only if it's not in the image of the Kuhlmann map. Okay, and in particular, well, I'm probably not actually going to explain it in this talk. You can use this sequence just by studying the slopes of UP on these two terms. You can use it to give a very kind of conceptual proof of Coleman classicality. But I won't really discuss that in this talk. Okay, so I want to just quickly try to make these spaces seem slightly more concrete. So, and maybe I'll especially focus on this one. So in fact, I mean, this space, it can be described in the following way, and it's really not hard from the definition. So it's a colimit over all levels at p, kp, and all opens U containing, well, I have to explain this notation, but so opens U containing what I'm going to call the canonical ordinary locus, but this is something that at a particular level was defined in Alice's talk, of the sections on this open. Okay, so this open, it's just, if you like, well, by making it small enough, it could be like an aphanoid open inside a finite level modular curve, and I'm just asking that it's a kind of strict neighborhood of a particular component of the ordinary locus. And which component of the ordinary locus is that? Well, the point is that if I look at pi Hodge-Tate, going to P1, so inside this there's the ordinary locus, well, some definition of the ordinary locus. There's kind of two meanings of the ordinary locus, but which maps to pi1 QP, the rational points of the Hodge-Tate flag space. And really what we're doing is we're choosing one point, infinity of this, and only working with that. And so, for example, if we try to work at finite level, we'll have a map xkp kp, which I'm going to call pi Hodge-Tate k lower p, which goes to P1, but maybe modulo kp. And just think about it as a topological space. And what we can do is we can take the kind of orbit of infinity in here and define its preimage to be xkp kp ord. And so basically the picture is that we're just choosing sort of one component, or maybe it's really a union of components, of the ordinary locus, the ones which map to this chosen point infinity under pi Hodge-Tate. Okay? And so, for example, Alice was talking about sort of x naught of p, and there was this picture. Well, I'm not as good of an artist, so I'm going to draw it as a genus zero curve, although it probably isn't. And so in this picture, the ordinary locus had two components. There was this kind of well, I think Alice called it the multiplicative ordinary locus. And then there's this other component, which I'm going to call non-can ord. And the idea is that sort of under pi Hodge-Tate, this is kind of mapping to the orbit of infinity, and this is mapping to the sort of orbit of 0. And there's only two orbits of kp on P1 QP. And that's explaining why there are two components of the ordinary locus at that level. And so the picture is that if we kind of just fix this level, we're taking some kind of strict neighborhood, and we're taking a colimit over all those strict neighborhoods. And the only difference in this definition is that we also want to do this thing of also taking colimits over all levels at P, just to put all the spaces together exactly like we did with the classical forms. Okay. So maybe that's enough about that. Ah, sorry. Yeah, I meant to write can. Sorry, thank you very much. Yeah, sorry. So this would be exactly the preimage of this point. Yeah, thank you. Sorry? Yeah, maybe I'm assuming this too. Yeah. Okay. All right. So that's what I want to say about coherent cohomology, I think. Actually, well, maybe I should say one more thing. So we had this like smooth representation of GL2QP. So of course, GL2QP doesn't act on these spaces, but rather BQP, which is the stabilizer of infinity in GL2QP, acts smoothly on these two spaces. And there's a similar formula where you take invariance under subgroups and you get the finite level over convergent modular forms, which I don't write. And maybe the last thing I should say is that, of course, like these classical cohomologies, they don't really come with any topology. They're just colimits of finite dimensional vector spaces. But of course, these spaces really have some kind of topology, although I'm not really going to mention it very much. And it's exactly coming from this formula, which expresses it as a colimit of Banach spaces. Or, well, if I took that U to be like a quasi-compact open or an affinoid open, then it would be. Okay. Sorry, is there?
Can you recover the space of functions on the whole ordinary opposite space functions?
Well, I think it kind of depends what you mean by that, but you have to be a bit careful because anyways, P1QP, it's kind of dense in P1. So you have to decide exactly what you mean. If you consider like the product of the stocks, then you can just induce and get a representation, but that's not really what this, let me not try to answer this further, but sorry about that. Okay, so I want to now move to the Betti side. And so I try to be brief because I kind of already talked a lot about this, but I also realized when preparing this talk that there were some things I should have said. But anyways, let me just kind of mention the setup. So we're considering the completed cohomology, and maybe I'm going to even stop writing the KP, so I'll just write the coefficients. And so this completed cohomology is, well, I gave several ways to define it, but let me just recall one of them. So it's a it's a limit over S of a colimit over K lower P of HI et YK Q bar of Z mod P to the SC. And let me recall one other formula we had for it, although actually I didn't quite write this formula, but well, I should have maybe. So I explained that you can compute this completed cohomology on the perfectoid Shimura variety, and so there it's HI pro étal X KP with ZP coefficients. Okay, and so what are the kind of analogs of the spaces of classical and p-adic modular forms in this case? So what I'm going to do is I'm going to also define HI tilde LA to be the locally analytic vectors in HI QP, HI tilde QP. And so for the modular curve, it's really only the H1 which is interesting. I'll say something briefly maybe about the H0, or maybe I won't because I'm going a bit slow, but it's really only the H1 that we're interested in. And so the kind of spaces that we want to consider, so there's the kind of classical forms. And so this is going to be, we're going to take K to be a non-negative integer. And associated to that, we're going to get a representation, which I'll denote by LK. And this is the sort of highest weight K representation of GL2. So this is just this representation, sim K. And we can take G-HOMs from this representation into completed H1. And so I really kind of need to explain why, but I will in a sec that this is basically the classical H1 of the local system corresponding to this representation and taking the colimit over all levels at P. So that's my sort of classical forms. And the sort of p-adic forms. Sorry?
Small g.
Yeah, I'm going to keep using this notation, but yeah, G is the Lie algebra. Maybe I should just say that. So it's Lie algebra which acts on the locally analytic vectors. So we're just going to take a kind of another representation of the Lie algebra. So what we're going to do is we're going to take nk to be the Verma module. And so what is that? It's some kind of induction of Lie algebra representations. So here, B inside G is the upper triangular Borel. And maybe I should, well, okay, now my board work is terrible. This K is just going to be a character of this Borel. And it's the one which sends, so I'll write it explicitly, it's the one which sends this element of the Borel to K times A. Okay, and if you like, this is sort of meant to be like the highest weight of this representation, Lk, when K is bigger than or equal to 0. Okay. And now what we can do is we can Hom, again as G representations, this Verma module Mk into first completed cohomology. Okay? And because this Verma module is induced, there's another way of writing this, which is the way Van Sant wrote it in the introduction, which is that we can also write this as Homs as B modules from this kind of one-dimensional representation given by this character into the first completed cohomology. Okay? And I think Van Sant explained in the first talk that sort of the goal of p-adic Eichler-Shimura theory from Louis Pon's point of view is to compute this space with its actions. And yeah, maybe I should have even, well, reminded you, but of course it has an action of GQP. But I'll write it here. This has an action of GQP, and it has an action of BQP. And sort of again, we don't really get, like in our spaces of p-adic modular forms in the coherent setting, we don't really get an action of GQP on this space because somehow we kind of fixed this Borel. And so this thing, it's only kind of a representation of B and not of G. But it does have an action of the Lie algebra of G. Okay? And so as over here, so okay, and I guess the thing I should say is that so of course this makes sense, this also makes sense, like this character I could just take K to be in CP. So okay, but for today I'm always going to take it an integer. Okay, and so kind of as over here we have this map from classical forms to p-adic modular forms, and you have an analogous map between these two things. So what's the relation between the finite dimensional algebraic representation and the Verma module? So we have a map Mk to Lk whenever K is bigger than or equal to 0. And that's just the map which sends the sort of generator of this Verma module to the highest weight vector here. It's surjective. And so dually, we get a map which goes from the Homs from Lk to Homs from Mk. Okay? And in fact, so, I mean, here you really had more than just this map. You really, for example, assume that K is like, K is bigger than or equal to 2, so this thing is 0. You really have this kind of complex computing classical forms in terms of a map between p-adic modular forms. And you'll get a similar complex over here. So I'll just say it here. We can also consider the resolution. So this surjection has a kernel, and the kernel is again a Verma module, but now of negative weight. Sorry, 2 minus k. And so if you like, you can try to harm this, except that, well, maybe you won't always get a short exact sequence. You have to be slightly careful about exactness. But you will if k is not 0, for a reason that I want to briefly indicate right now. So, yeah. Move this one up. Okay, sure. Yeah, so I learned my lesson last time about trying to use the 3-cycle technique, and I think that the Ben Howard technique is much better. Okay, so I want to quickly clarify 2 things, although I probably won't say this in much detail. But this is going to help you understand, well, something that will happen later. So the first thing is sort of why is this, the thing that I'm calling the space of classical modular forms, the space of classical modular forms? So why do we, what does this actually have to do with the classical Betti cohomology? And the other thing is, so later on, we want to derive everything, and it's for a good reason. So which I'll explain when it happens. And so in particular, I'm going to stop writing these HOMs as G modules from a representation into H1, and I'm going to start writing expressions that look like R HOM G, well, M, where M is one of those 2 modules, into sort of R gamma tilde LA, which is like the complex of completed cohomology. And so I want to explain that actually, usually, sort of nothing here is derived, and you're really just getting the thing that I wrote over here. Okay? And so I'm going to try to do this very briefly, and maybe this will be explained in slightly more detail in the notes. But the point is that, okay, the modular curve only has H0 and H1. So there's no higher cohomology. And moreover, the H0 is actually pretty stupid. So what is the H0? Well, okay, I shouldn't call it stupid. That's not very nice, but it's not very interesting. So what is the H0? So basically, it's the well, it's the, let me just write from the definition. Functions from sort of pi naught of the modular curve at this finite level Kp with values in z mod p to the sc. And so what is this set or actually group of components? Well, I mean, there's a classical description, which I'm not really going to recall, but probably this is something that most of you have seen, which is that it can be described as a kind of quotient of the units in z hat by the determinants in the level. Okay? And so what that means is that when you compute this completed H0, you're really just getting continuous functions on this z hat cross modulo the determinants in the tame level. Because this is somehow the limit of these things over, sorry, why did I write that? Over k lower p. With values in zp. Oh, I didn't say what are the coefficients. Okay? And so in particular, the action of the group GL2ZP is just by determinant. Okay? And so that means that the action of the Lie algebra of G factors through sort of G mod the derived group. Okay? Okay, and so last time I explained this Hochschild-Serre spectral sequence, and if we take sort of colimit over Kp of the Hochschild-Serre spectral sequence from last time, you get a another similar looking spectral sequence, which I really should have written last time. But somehow I talked about locally analytic vectors after I talked about this, so I didn't. And basically, it looks like this. So you consider sort of Rham of G of, say, this Lk into, I'm supposed to be writing a spectral sequence, sorry. So this should be X_p of G of this algebraic representation into H completed Q LA, and this will compute the sort of the colimit over Kp of the classical cohomology associated to this local system. So the colimit over Kp of Hp plus Q y Kp Kp, and then the local system, well, actually associated to the dual of this representation. Because when I wrote this the last time, I put Lk on that side, and now I put it on that side. Okay? And so a consequence of this spectral sequence and this spectral sequence, sorry, not this description of H0, and I'm not really going to explain this very carefully, because I need to talk about p-adic Eichler-Shimura, is that, so as long as if I compute the sort of the derived thing, so Rham G M into R gamma twiddle LA, this is, well, really both of these functors are kind of underived. So basically you only get Hom here and H1 here. So this is really just the kind of thing I was writing before. And this is basically what I wanted to say. Hom M H1 twiddle LA in degree 1. Okay? So let me not explain how to prove this, but I'll just say in kind of words, really all you should do is use that, basically, this computation, it tells you how the center of the universal enveloping algebra of G acts on completed H0. And so the modules that I've written down here are exactly the ones where that action is not through the trivial character, whereas on H0 it is through the trivial character. And so for those ones, there will be no interaction between M and H0. And that's basically the proof. And then you have to think about what degrees the total cohomology is supported in. Okay. Anyways, that probably wasn't very clear, but I also felt like I should really say that, because from now on, I'm always going to be writing this derived version of these spaces. Okay? Okay. Time for p-adic Eichler-Shimura, finally. Okay, so what is the goal? So the goal is exactly to compute these things. So we want to compute Rham G M R gamma twiddle LA tensor CP together with its action of GQP and its action of BQP and maybe its action of some Heck algebra away from P. We want to compute these in terms of the coherent things from before. And classical p-adic modular forms. Okay? And so what I'm going to first do is I'm going to basically outline the steps in this computation and then really do my best to explain something about one of them. Okay? So maybe I should go to one of the sideboards because then I can. Sorry. Oh, yeah, sorry. So GQP is the Gawa group of QP. I'm really sorry. This is another abuse which is constant in the subject, and you have to deal with it. I don't know. Some people write gamma, but yeah. Sorry. Yeah, so this is the Gawa group. This G has nothing to do with GL2. Yeah. Whereas this B does have something to do with GL2, but yeah. Okay. Okay. And actually, maybe I should just stop and ask if there are any questions about all of this before we. Somehow this was my overview of p-adic, classical and p-adic modular forms. Yeah? Right, so I mean, so it's a complex in this abelian category of admissible locally analytic representations, if you'd like. Yeah, so it's legitimate to do this, although we'll do something a bit scarier later on. It's legitimate to do this because there's this theorem of Schneider and Teitelbaum that taking locally analytic vectors in admissible representations is exact. Okay? Any other questions? That was a good question. No? Okay. Okay, so let's get started with that. So I want to explain basically what you do to compute this. Okay, so I'm going to state a lot of steps, and some of these steps are kind of easier to justify, some of them are harder to justify, and I'm just going to go through the whole argument without really explaining any of them. So step one is that we just want to bring the CP inside, and probably I should be writing some kind of hat here. I'll probably forget to write hats on a lot of tensor products in this talk, but this is really some completed tensor product. And so indeed, we need to be a bit careful about what are the topologies on this space and this kind of thing, and I'm going to be quite sloppy about this in these talks, or in this talk.
Maybe just back to the question that they asked.
Yeah.
R gamma tilde LA.
Yeah.
So it's the same. The H I tilde was this limit and colimit of étal cohomology groups.
And then you take locally analytic vectors.
Replace H I étal by R gamma étal.
Yeah.
Print as a complex, and then you just take local unity vectors of each terms of the complex.
Yeah.
Correct?
Yeah. Okay, so step one is we're going to bring the CP inside. And actually, we're going to bring a lot of things inside, and that's kind of the point of this computation. So we're just going to say that Rham G M R gamma twiddle LA tensor on the outside with CP is really the same thing when you just bring it inside everything. Okay? And again, one needs to be a bit careful about topologies and all of these things, but it can be done. Okay, so that's step one, and this is not very hard to justify. Step two, so the idea is we want to make coherent cohomology appear, and right now we have Betti cohomology, and so we have to do some kind of comparison at some point, and we're going to do it right now. We're going to rewrite this using Schulze's primitive comparison. So we use the primitive comparison, and really also the fact that xkp is perfectoid. So what that tells us, so we know that the completed cohomology with qp coefficients tensored with cp, well, we know that the completed cohomology with qp coefficients is the same as the pro-étale cohomology of the perfectoid modular curve with qp coefficients. And then we tensor with cp. And now the primitive comparison tells us that we can write this pro-étale cohomology as just sort of coherent cohomology of the structure sheaf, the completed structure sheaf. So I'll write just once R gamma n. I really just mean the cohomology for the underlying topological space of this completed structure sheaf. Okay? Okay, but so we've now managed to kind of get coherent cohomology to appear in this computation, but you should really think that the coherent cohomology we want is not the coherent cohomology of these completed sheaves, so sheaves on sheaves of O(x)kp modules, but rather we want sheaves of O smooth modules. So we have a lot of work to do, and there's still the locally analytic vectors and the g-HOMs to help us out. Okay? And maybe I just rewrite again that now this is sort of isomorphic to this R-HOM G of the locally analytic vectors in this. And I'm not going to write this an ever again. Oh, sorry, my m is not there. Apologies. Okay? Okay, so the next thing to do is to observe that taking cohomology is a very violent thing to do. And so what we're going to try to do is do the other things first. So we're taking this locally analytic vectors and we're taking this Lie algebra cohomology. So step 3 is to take cohomology last. Okay? So what we're going to do is we're going to first bring the locally analytic vectors into cohomology. So let me just write that part. So we're going to say that Kp LA is equal to R gamma xkp OLA. Okay? Which is very believable, but I already insist that this is highly non-trivial, and I'm not really going to explain how to prove it. But the key thing is to show that, well, so the basic problem is with taking locally analytic vectors of this sheaf, because if you look at OKP U for U some quasi-compact open, and you look at the action of some Kp which stabilizes this U, so this thing is enormous. It's not an admissible representation. Okay? And so the key thing, well, depending on how you phrase it, the key thing is to first of all understand how to take some kind of derived locally analytic vectors here, and then to prove that actually there are no derived locally analytic vectors. So the key thing is basically to prove that, that sort of the underived locally analytic vectors are the derived locally analytic vectors. And this is the thing which is defined by Joaquin Rodriguez with Juan Esteban Rodriguez Camargo in their very nice work on locally analytic representations from the point of view of condensed mathematics. Okay, and I'm not going to make any attempt to explain this, but I'll just emphasize that there's really something to prove here, and it uses the stuff that Vincent talked about last time. Okay. On the other hand, it's very believable. Okay, and then we're going to do the same thing with the kind of Lie algebra cohomology, or the Rham-G. Yeah. Yeah, I believe, yeah, so if you derive the locally analytic vectors everywhere, then it's essentially formal, and so the key thing is to check that you don't have to derive the locally analytic vectors. Yeah. Or then you could ask, well, why don't I just work with this RLA even if there are derived locally analytic vectors? But okay, well, you're going to wind up proving this anyways, and it's sort of part of the thing that Vincent has discussed anyways, so. Okay. And so then we'll do the same thing with this, and so let me just write the kind of final formula, which will be that, so the thing that we're trying to compute is now isomorphic to, so we take cohomology as a last step, and it's with coefficients in some sheaf, which involves first taking R gamma Lie algebra Hams, or sorry, this should be R Ham G M into the sheaf OLA, okay? And you're welcome to be feeling a little bit nervous about what kind of object this is, okay? Okay, so now we basically come to the key point, which is that we have to compute this sheaf. I'm actually a bit confused. Somehow I thought there were more steps. Did I screw something up? Okay, too many pages. No, it's the right number of steps, sorry. Okay. Step 4, we need to compute this guy. Okay? Okay, and in fact, well, for these M's, like these Verma modules and algebraic representations, this is going to be computed in terms of the sheaves of overconvergent modular forms. And I'll just write down essentially the answers later, but in terms of these sheaves of O-smooth modules. So the modular sheaf and also the ones produced by excision. Okay, and this is kind of the miracle of the subject, is that you compute this and you compute it in terms of these things. Okay? And so how are we going to do this? Well, the idea is that we really need to understand something about the structure of the sheaf OLA. And conveniently, that was exactly what Vincent's lecture was about. Yes? And so I'm going to tell you a kind of like incorrect version, or a simplified and incorrect version of the thing that Vincent proved. I mean, more or less, he was telling us that sort of we have O-smooth, which behaves like a one-dimensional object, and then the sheaf OLA, it kind of behaves like a four-dimensional object, and there's sort of 3 extra variables over O-smooth. And so the sort of incorrect statement of the structure of OLA. So I can't emphasize enough that this is not correct, but it's a good fantasy to have, and I encourage you to just kind of understand the argument this way, is that somehow you get OLA from O smooth by basically just adjoining 3 extra variables. So really only makes sense to take this tensor product over CP. And here I should just take, well, it doesn't really matter. It should be like germs of analytic functions in 3 variables, but since I'm saying nonsense anyways, it doesn't really matter. I'll just write a sort of convergent power series in 3 variables. Okay? And now, so we're trying to compute this Lie algebra cohomology. And if you believe this formula, which is not true, the action of G on here is trivial, because these are smooth vectors. And so all the action is just on these kind of new coordinates of OLA. And in some sense, this is kind of explicit. And so if you believe that, it's basically telling you that all you have to do is kind of do some computation which involves this module M and the Lie algebra action on these 3 variables. And that's some purely local computation which has nothing to do with Shimura varieties. Okay? And this is essentially how it works, just a little bit more complicated. And so now I try to kind of explain the correct statement of this, and then I'll try to explain the statement of p-adic Eichler-Shimura, and maybe try to explain some computations. Any questions about the sort of fantasy argument? And by the way, just to say, you might imagine that there's some module M for which this R-homing M into this thing is like literally just asking for constant functions, and you're just getting O smooth. Yeah, so you should view this as, yeah, so this space of functions, it kind of already is a space of functions in 4 variables satisfying some differential equation, and then we're kind of imposing some more. Yeah. Yeah. And I apologize, there's some GL2 versus SL2 confusions, which I'm just completely sweeping under the rug. And if that's bothering you, you can.
Here is 3 because it's GL2 or
Well, it's 3 because it's 4 minus 1. So basically, like, the what?
So it's GL2.
Yeah, it's GL2. But maybe, well.
Like 4 is the dimension of GL2.
Yeah, so 4 is the dimension of GL2. Yeah. And then the sen operator, although that word was never used, kind of kills one of them. Okay, but I recall the thing that Vincent wrote. Sorry, Vincent. Sorry? Yeah, it doesn't kill the center. Yeah. No, I'm more just saying that I'm writing down representations of SL2, and when I really mean representations of GL2. Sorry. Okay. I really shouldn't have said this at this point because it was probably very confusing. Okay. Okay, so let's try to write down the correct thing. Okay. So let me recall the things that Vincent explained in the last talk. So first of all, we have this local description of OLA, but it's a bit more local than the fantasy one I'm writing over here. So it's given by this admissibility formula, and the idea is that you kind of base change OLA to itself. And this is isomorphic via a map. I'm not going to remind you what it is, because I just want to write the formula, to this sheaf on the flag variety, which is, well, I'll explain all the notation after I write it. Sorry, tensor with CP with OFL. And then you take this U0 equals 0. And so now this is still a sheaf on the flag variety, and so you tensor it over OFL with OLA. And so, roughly speaking, what my fake formula over here is supposed to be is I'm basically taking like the fiber of this thing at one point of P1, and then I'm just pretending that I can kind of cancel out the OLAs. But it doesn't really make sense. Okay, so let me just remind you what are all these terms. So OG dagger. So this is like this is the stock of OG an at the identity, which is concretely just germs of analytic functions in 4 variables. Okay, and this U0, so I remind you that we have on OFL, which is P1, so on FL equals P1, we have these Lie algebras, U0 inside B0 inside G0, where G0 is just G tensor OFL, so it's the constant Lie algebra G on the flag variety, but these things are not constant. They're basically just the sort of tautological sub-Lie algebras of this. So for example, this would be like X inverse Lie, well, let me just write it. It would be like X inverse U X over the point B times X.
So here is G an or G LA?
Sorry, this is an an, sorry.
Yeah, it's not LA.
No LA, yeah. But this thing is, well, anyways, yeah.
But it's
G is GL2, yeah. Sorry, it was GL2 from the start, yeah. Okay. And so, yeah, I just repeat the thing I said before. Basically, yeah, so this thing, it's like germs of analytic functions in 4 variables. When you impose this differential equation, the fiber over a point of FL will be germs of analytic functions in 3 variables, and that's what I kind of pretended we had over here. Okay. Okay, and so Vincent also explained that there's this functor VB, which goes from, well, I'll write the scary thing and then I'll explain how you should think about it. So it goes from this category QCO, which is probably really have to be some derived category, of sheaves on this twisted de Rham stack of the analytic P1. So that's scary. And it's going to sheaves of O-smooth modules, which is the kind of thing we ultimately want to see at the end of our computation. And what is this functor? Well, I'll write the functor and then I'll remind you what is this category even, or how you should think about it. So this functor, it sends an object of this category, whatever it is, to, you basically tensor with OLA over OFL, and you take the smooth vectors. I think Vincent wrote you take the invariants for G, but that's the same as taking the smooth vectors. Okay. So, yeah, it is really beyond me to explain the actual definition of this category. And for example, I don't know if there's this, whatever this is, has a T structure or anything like that, but it's something which has been defined. But really, there, for example, are some more old-fashioned definitions of what you could put here, which I'm also not going to recall, but I'll just tell you how you should think about it. Basically, these are some kind of sheaves on OFL, so quasi-coherent sheaves. I probably should say that. So there's some kind of quasi-coherent sheaves on OFL with a G naught action such that U naught is 0 on it. some kind of analytic twisted D module. Okay? And so there's a lot of subtlety in figuring out exactly what you should put here, because we're going to want to consider some objects in this category which are kind of big, so they're not like coherent sheaves on OFL. And since we're working in analytic geometry, we need to account for some topology. And really, we don't really just want an action of the Lie algebra, we want an action of the Lie algebra which kind of locally integrates. And so maybe it would have been better to write with a kind of G dagger mod U dagger action, or U naught dagger action. But I just write the exact same thing Vincent wrote. Yeah. Right, so basically, there's this thing that I said in words, but I didn't write, which is that you have this Lie algebra action, but we're really assuming that it locally integrates. So basically, like any section of this sheaf, it's going to have an action of a kp for p sufficiently small, because the action is locally integrable. And this has an action of kp, and you take the diagonal. So that's why Vincent wrote, yeah, I mean, maybe I just write the thing that Vincent wrote, because anyways, this has an action of G. Yeah, that maybe makes you more happy. Okay, and then we had this kind of admissibility formula, which says that VB O times O smooth OLA is the same as F O times OFL of OLA. Okay, so yeah, I'm supposed to go up there. Okay. Okay, so this all sounds a bit crazy, but I just want to write down some objects in this category and tell you what the functor does to it. So, some objects. So, the first one is, where has it gone? So there's this one up here, which is appearing in this formula. So, there's this thing that I'm just going to call CLA, because that's what it's called. So that's an object in this category, and that formula is basically telling us that VB of it is OLA, okay? And this is an example of what I mean when I say you really have to allow big sheaves, because I mean this is somehow the fibers over a point of FL are really these like germs of analytic functions in 3 variables. So it's not like a coherent sheaf, it's really a quasi-coherent sheaf with some topology. Okay, but then there are some nicer objects. So Vincent mentioned at the end of his last lecture that the sheaves OP1 of K, and again, I'm not going to be too careful about SL versus GL here, so SL2 versus GL2, so I'll just write OP1 of K. So these are in this category, and VB, well, I think Vincent said something like unsurprisingly, sends them to the smooth sheaves. The smooth modular sheaves. And similarly, the same thing happens for the kind of X-sized sheaves. So we can consider these kind of sheaves, and I'm going to be honest with you, working in this category, I probably shouldn't be writing the functors like this, but I'm just going to write the topological ones because, anyways, that's what we do in the paper that we wrote. And so these ones basically map to the corresponding things. Okay? So those are some examples. And we need one more example. And then I'll basically state all the theorems. And so there's a functor, which is some version of localization which is going to go from, well, let's just write it as G modules to, well, this category of, well, whatever it is. And what this functor is that you take your G module and you map it into Rham G M CLA. Okay, and really I have to tell you what action of G am I using on CLA. And so here, G acts on CLA. Well, let me just write the definition of CLA again. Via the sort of right action on G dagger. And so in particular, this action is kind of OFL linear. So it's just acting on the functions on the fibers. Okay. So now I can state the theorem, which is the correct computation of this thing. So it says that Rham G M OLA is equal to VB log M. Okay? And okay, I was prepared to present a short and unenlightening proof of this, and I think I'm just going to not do it because I want to state the main theorem. Okay. And unfortunately, I have to explain one more thing before I can state the main theorem. So, and this has to do with the GQP action. So we need one more bit of structure on objects in this category. And maybe I'll start on a new board. Why do I call it log? Yeah, so, well, I'm going to write down some computations when I have like -5 minutes. Well, okay, I try not to go very over time. But so this functor, it's extremely closely related to valence and Bernstein localization. But I have so little time that I'm not really going to explain how. But basically, like valence and Bernstein localization is like you take a UG module, you tensor with the flag variety, and then you take either U0 or B0 invariance, depending on whether or not you want the sort of twisted version or the fixed weight version. And here we're kind of doing the same thing, except we're taking, sorry, in valence and Bernstein you take U0 co-invariance. Sorry. Here we're taking U0 invariance. So it is kind of dual to the valence and Bernstein situation. Well, that probably means nothing, but I said it anyways. Okay. So I need to talk about this horizontal Cartan action. And my timing is not great, so I'll be pretty brief. So we have these sheaves of Lie algebras, and we can consider what I'm going to call H0, which is B0 mod U0. So this is a sheaf of Lie algebras on OFL, but by some slight miracle, it's actually a constant sheaf of Lie algebras. So this is actually just OFL, or let's write P1, O times H, where sort of H is just the torus in the Lie algebra. And, okay, maybe I was prepared to say something about how you can see that for GL2, but I don't have time. And also, Vincent said it in the questions yesterday. And so we also, so what this basically tells you is that whenever you have a sort of G0 mod U0 module, you get an action of this horizontal Cartan. in Q-co FL de Rham twiddle. Okay, and I'm just telling you that because it's going to appear in the theorem. But I should go over here. Okay. So now I'm just going to state the main theorem, which kind of puts together this computation plus the 4 steps. So the theorem says that we have, so for m equal to this Lk or Mk, we have an isomorphism. So the thing that we wanted to compute, so Rham G, Mk, sorry, just M, R gamma twiddle La O times Cp is equal to cohomology xkp of that sheaf. So VB loc M. And so this is a isomorphism of BQP times TKP modules. And also, well, let me just say GQP modules, but I have to explain how does Galois act on this side, and that's where this horizontal Cartan comes from. So where the sen operator, so this is some kind of huge CP vector space, so you can imagine it has a, with a GQP action, you can imagine it has a sen operator and is given by this mu inside H, where mu is the Hodge cocharacter, via the horizontal action. Okay. So that's the theorem, and I really feel obligated to just give some brief examples. But okay, so the point of this theorem is that we haven't actually solved the problem yet. We've just reduced it to computing loc M. But now this has nothing to do with Shimura varieties. It's really actually closely related to just computing something like Balins and Bernstein localization. And let me just tell you, let's do 2 computations and then the 2 consequences for cohomology, and then I'll stop. So, but I won't do the most interesting one because now I'm out of time. So let's consider, so this is sort of computations. So I apologize for going over time, but this is probably actually the more interesting part of the talk rather than the last bit. So let's consider these algebraic representations. So for k bigger or equal to 0, loc Lk is, well, I have to write the right thing, but it's O of k plus 2 in degree minus 1 plus O of minus k in degree 0. And this might look extremely weird if you're familiar with Balins and Bernstein localization because it somehow feels like it's flipped, but let me not comment on that. And just go ahead and write, so let's do the kind of negative weight case, which is sort of less interesting. It's really the positive weight case, which is interesting, but let me just tell you what is the localization of the Verma module in negative weight, because that's where you get the kind of cleanest p-adic Eichler-Shimura isomorphism. So this is going to be the same thing, except with some of the excisions operators applied. So we're going to get I lower star, I inverse, OK plus 2, again in degree minus 1, plus this with the J lower shriek, J upper star. Okay, I hope I got that right, but Vincent will yell at me if it's wrong. And let me just now state the consequence. So if you just combine this computation with this theorem, you get corollary. First, in the algebraic case, you get the sort of Hodge-Tate decomposition of faultings. So if we apply this, we get that, well, I write it in the sort of ridiculous way, but it's the same statement as the, so we get that sort of hom G LK H1 twiddle LA is the things which I defined really a long time ago, these spaces of classical modular forms. So this thing, so we're taking an H1 of this thing that I'm deriving, so I get an H naught of this, which is going to give me the weight k plus 2 classical modular forms, and I have to account for the horizontal Cartan action, which I'm just going to magically tell you is giving us this Tate twist, plus, well, the H1 of weight minus k. So that's the kind of classical Eichler-Shimura decomposition, taking a co-limit over all levels at p. And we also have corollary due to Pon, and of course in the finite slope case, there's similar results proved in Andrade, Irobita, and Stevens, and in the ordinary case, there's results of Ota. But I think this formulation of it is in Pon's work, which is that hom G, so I tell you only the case where m is less than minus 3, and that's to avoid, I'm avoiding minus 2 because of this issue with the H twiddle naught. And so I get exactly the kind of direct sum of the corresponding two spaces of p-adic modular forms. So this kind of, so k is negative, so this is negative weight over convergent p-adic modular forms with the same Tate twist, which is now positive, plus H1 W naught minus k. Oh, and that's probably telling me to stop, so I stop.
Okay, I don't know if there's one question.
Yeah.
Our is very simple, I guess, so
yeah.
It's nice because we can sort of compute, I think.
Yeah.
It's in the more general case where it's really a complex, I mean...
Yeah, so it's true that in general, like, there can be lots of degrees of completed cohomology, and it can make this thing kind of complicated. Although there's lots of things you can do to make completed cohomology be only in one degree. Like you can make a localization like in Karini-Schulze, or you can use this amazing theorem of Luai-Pan and Kaiwen-Lan, which basically is a generalization of this thing I told you about H naught twiddle. They basically prove that as long as you localize at a sufficiently regular infinitesimal character, the completed cohomology is only in the middle degree, the locally analytic completed cohomology. And so if you do those kind of things, you do get kind of less derived statements. But in general, it's better to be derived. And I really probably should have said it, but like the point is this functor loc m, and this computation at the level of the sheaf, wherever it is, I don't know, has it been erased? Like the computation where you R hom m into OLA, like in general, there's higher cohomology there. It's only after you take cohomology at the end that there's cohomology only in one degree. Yeah. I mean, sorry, you see it like in this formula, right? Like here, this is really in two different degrees. But then you take cohomology and they magically become in the same degree again. Yeah.
Okay, I think we have to go to lunch. So we thank George again.